Hello everyone, good morning, good afternoon, good evening. I am Riddhi Gohel as a host of ICICT 2022. Dear authors and invited guests, welcome to the technical session 4E. On behalf of Global Knowledge Research Foundation, it is my great pleasure to welcome you to the 7th International Congress on Information and Communication Technology through Zoom. Further, as you are well aware, we have been facing new normal situation while overcoming the pandemic. Hence, the conference has been shifted to a hybrid mode. We are very thankful to everyone present on this platform to go along with digitally for the conference in these unpredictable circumstances of COVID-19 and making this conference more productive. Also, we wish everyone and their families has a protected time. Also, there is a special note for the presenter. You will be given 10 to 12 minutes for your presentation and 2 or 3 minutes for question answer. On 10 minutes, I will raise a general reminder. And I request while the presentation is going on, all the other participants kindly be must muted. There is another request to all participants that you are all stay connected with us till the session not ending. Just before we get started, I would like to introduce all our session chair, Dr. Nityesh Bhatt. He is a professor and chairperson of information management area at Institute of Management, Nirma University, Ahmedabad. He holds MBA and PhD degrees from ML Sukhadiya University, India. He has also completed a 4 months faculty development program of IIM Ahmedabad and an online internet governance capacity building a program of Diplo Foundation, Malta in year 2006. He has more than 22 years of experience in academia, corporate training, research. He is a member of National Executive Committee of Special Interest Group on e-governance set up by Computer Society of India. He is a lifetime member of Computer Society of India and Indian Society of Training and Development. His research domain are e-governance, e-commerce, and enterprises allocation.
Thank you, Riddhi, and good afternoon, good morning, good evening, depending on your respective times. I, Nityesh, but welcome all of you to this ICICT, 7th ICICT, along with the Excellence Awards which are going on. And this event is being organized by GR Foundation along with other agencies like IFIP and so. So without wasting much time, I welcome all of you, and we want to start the academic presentations by all the esteemed academicians who have gathered here from across the globe. And the first paper is from Jay Koetzer. Is he or she here?
Yes,
Yeah.
I'm here.
Yeah. So all of you can see the paper, the impact of collaborative decision making in a smart manufacturing environment. So here is a case study. I welcome the author to please present it, and I request all of you to please adhere to the timeline, 10 to 12 minutes for presentation, and I request all of you to raise questions if there are any, and if you want to add something, that also can be done. So thank you, and over to you.
Thank you, Doctor. I'm just going to share my screen.
Yeah. Yes, ma'am, please go ahead.
Can you see my screen? Why doesn't this want to now?
Yes, we can see, and you are audible. Please go ahead. Please
Alright.
run it in the slideshow mode so that the fonts are better visible.
Yes, I'm having a problem to.
Ma'am, can we request you to please turn on your camera also? While it is better if everyone can turn on their camera, but at least the presenter should do that.
All right, thank you.
Please go ahead.
Problem to start the slideshow.
Ma'am, please start. Please go ahead.
All right, I'm sorry, I am trying to share this. Okay, here it is. Thank you, sorry about that. So good morning, everyone. And thank you for the opportunity to present my work to you today. I'm just going to start with a small introduction. And then we will move on to the, sorry, I'm having a problem here to see my screen. I apologize. Okay, so the first part of my presentation deals with the introduction to the study, followed by an overview of the water bottling plant that we will be using as a case study. And then I will move on to the introduction of the collaborative decision-making to the water bottling plant. And finally, the results and findings are discussed and rounded off with a conclusion. All right. Okay, so let me just start by giving a brief background on the study. With the rapid advances of Industry 4.0 and the technologies, it has become clear that the automated systems in a manufacturing environment is increasingly taking over the production and manufacturing scene. So a rational consequence of this is the way in which humans and machines interact. And that may lead to the declining of human control of processes as the manufacturing processes become more and more complex and automated. But humans have a natural level of intelligence that is used in manufacturing systems, or that is not used in manufacturing systems currently. So the information flow between the human and the machine is crucial, and this can be achieved by using human-machine interfaces, allowing for such interaction. So with that said, a research gap has been identified, identifying the lack of processes involving collaborative decision-making, as the productive setup of an automated system relies greatly on the interaction between the human operator and the machine. For this research, a case study of a fully automated water bottling plant is used to determine the impact of collaborative decision-making to a smart manufacturing environment by introducing a human-machine interface to the system. Two potential models are presented, namely a machine-only approach and a collaboration between the human and the machine. Next, I will discuss the automated bottling plant. Now, the aim of the water bottling plant is to execute customer orders for the filling of 500 and 750 ml water bottles. The plant is split into 3 sections, where it contains subsection A, where the water source is located. Subsection B is for the bottle storage, and subsection C is for the water filling unit. Now, the input to the model is received via a web server through an interactive user interface, where customers can place their orders for the 500 and 750 ml bottles. An optimization model executes these orders and it uses 3 smart manufacturing units driven by PLCs and sensors. Let's just briefly look at the machine-only scenario. Figure 2 displays the 3 smart manufacturing units used for the water filling process, and both scenarios that we will be testing as part of this research will be done on Smart Manufacturing Unit 3, where the water filling takes place. The automated system must complete the task in optimum time, as orders are received via the web application. For the purpose of this research, only one constraint will be tested, namely the water level in the storage tank should ideally not go below 25%. The Smart Manufacturing Unit is programmed to automatically stop production when a level of 25% is reached and resumes when the storage tank has been replenished. Now let's take a look at the collaborative approach. To test the automated system for a collaborative approach, a human-machine interface will be created and attached to the smart manufacturing units. Figure 3 shows the setup of the water bottling plant with the 3 smart manufacturing units. Now, there are several places where the human can fit into the production line, but for this research, the human can intervene, will be placed at SMU 3 and can intervene between the water filling station and the capping station. To bring the human into the production process, a human-machine interface was developed, designed for human intervention. The HMI, or human-machine interface, is connected to a PLC that creates an alert and when the water reaches a certain level and requests whether the speed of the production should be slowed down or be sped up. At this point, an informative decision can be taken by the human for adjusting the flow rate of the water filling. The hypothesis is that the human system collaboration will enable faster decision making and therefore speed up the production as opposed to a machine-only scenario. Next, we will look at the preliminary results and findings. In these diagrams, figure 4 indicates the operation of the plant in a fully automated mode with a free run water fill. That means there are no constraints attached to the machine and to the system, and the machine makes all the decisions. This should, however, not be considered, as the water level should ideally not reach 0%. When this happens, the system comes to a complete stop until the tank has been replenished. Figure 5 indicates the importance of having interventions by either the machine or by the human for production optimization. A flow rate sensor and a water level sensor monitors the flow and the water level, and when the water level reaches 25%, the process slows down and waits for the water to be replenished. As soon as the water reaches a certain level, the production will then resume. If we look at this scenario, the total time where the machine controls the water level is about 1,100 minutes. Next, when we implement the collaborative decision-making approach, figure 6 and 7 shows diagrams of the operation of the plant where the HMI was introduced. So for the obtaining of a holistic view of the manufacturing process, the supervisory control and data acquisition system is implemented, and this allows for the human to have an overall view of the whole process, such as the water available, the water flow rate, the bottles in storage, and so on. In these two scenarios, the water flow will be delayed or slowed down, as seen in figure 6, and figure 7 shows the process of speeding up, as the human knows that the water returning to the tank is imminent. Now, this information is received from the SCADA, and this allows the human to make an informed decision.
Hello, sorry for interruption, ma'am. Last 2 minutes are there. Please summarize your work, ma'am.
I'm sorry, I couldn't hear that.
Yes, ma'am. Last 2 minutes. Then please summarize your work. Yes.
Thank you. Okay, so figure 6 indicates the slowing down of the process, where the water level reaches 10,000 mil or 25%, where the human can anticipate that the water is not enough and intervenes via the human-machine interface. And it slows down the filling, although the process will still continue. The completion time for this scenario is about 881 minutes. Figure 7 shows the ultimate scenario, where the water level drops and the system pauses as it's been programmed, but now the human intervenes again via the HMI to indicate to the system that the process can be sped up as the water is reaching the system shortly. The SCADA allows the human to see that the water is on the way. So the machine does not have to slow down, and the human interaction overrides the speed up of the process. And this whole process takes about 551 minutes. Now, the results that we are looking at is that the process of filling the water bottles takes time, and the ultimate goal of the production process is to complete the orders in optimal time. Figure 4 and 5 indicates the completion time for a set of orders as about 1,100 minutes in a fully automated mode. And figure 6 and 7 implements the human-machine interface, indicating the entire process for the same set of orders that took 881 and 551 minutes respectively. So the results as presented in figure 6 and 7 indicates that the collaborative approach was at least 20% faster than the machine-only scenario. In conclusion, the purpose of the research was to determine the impact of a collaborative approach between humans and machines in a smart manufacturing environment. The case study is the automated water bottling plant, and the two scenarios tested was the fully automated process and the human collaborative approach. Results showed that the collaborative decision-making approach was at least 20% faster than the machine-only approach. This applies to only one section, SMU3 of the plant, and not the entire functioning of the plant. So for future work, the research will measure the impact of introducing a collaborative approach to different sections of the plant. So there are some limitations. For example, identifying areas where the human contribution would hold value during the production process, and that warrants further research to arrive at an optimum process in an automated environment. Finally, I just want to say that we are not trying to prove that humans can be better than machines, but rather to determine whether humans are best suited in an automated manufacturing process. Thank you. These are some of my references and questions.
Thank you.
No problem.
Thank you. Other participants and presenters, if you have any question before I ask. Okay. So, ma'am, 2-3 questions I have. You can stop sharing, please, so that the next presenter can at least start presenting. Okay. So, first part is when you implemented this project, what was the cost of implementation vis-a-vis what is the benefit you got out of this?
Currently, the implementation is still happening. So I was not aware of the cost, as this is part of a big research project at our Center for Sustainable Smart Cities. So there's several projects that contributes to this project.
So cost you are not aware of, but what is the tangible benefit, financial benefit the organization got because of this HMI?
Well, the process of completing orders, customer orders in, the try and optimize the production of the output to the customers is actually quite beneficial to the institution, although it's still currently in process. And so there's actually still a lot more to come. This is just the preliminary findings.
So this will be worthwhile to study the impact in customer satisfaction, new orders.
Yes, yes.
Right, your market share, something like that. The next question which I have is, it was implemented in one of the SMU, you said.
Yes.
What will be the challenge when you try to implement it, let's say, in all the 3 or other plants also? Scale it up.
Scale it up. First of all, the water filling station looks at the water levels, but when you have to carry on to the next station is where the bottle capping takes place. So the system will have to distinguish between the 500 ml and the 750 ml bottles. That is quite a challenge to implement that, and also to see what the impact will be for the operator, the interaction that will happen there. So bottlenecks can happen, so the human can intervene and make a switch there. And then the third SMU will be for the packaging of the bottles. So different sizes of bottles will be packed into the respective orders to be able to send them to the customers. So
okay,
yeah, we are in the beginning phases of this.
So I can see your name, it's a Jean Markram something, and here its name is J. Koitzer. So it's the same, or you are co-author?
Yeah, no, that's me. Sorry, that is my maiden name. Markram is my maiden name.
Okay, okay, okay. So thank you.
I don't know
thank
why.
you.
Yes, thank you so much.
So are you a faculty working somewhere?
I am a lecturer at the Faculty of Engineering,
Okay,
Information Technology.
Great, great. Thank you very much.
Thank you so much.
It was a wonderful case study. And now I request Professor Ali Abdel Kader, who is going to present his paper titled Camera and LiDAR Fusion for Point Cloud Semantic Segmentation. Over to you, Mr. Ali.
Just a second. Yes, sir. I think Neha ma'am will come. Neha ma'am?
Am I audible now?
Yeah, Neha,
Yes.
you are audible. Welcome.
Okay, so I'm so sorry, everyone. Today also I got a very important lesson that like life, technology is also very unpredictable, and we really have no answers to certain questions, that why something which is going on so smoothly just stopped going our way as expected. So I'm really sorry, sir, and others to not start the session as expected, but I'll really try my best to make it up in the meantime. So sir has already invited the second presenter of the day. So I would request the presenter to please start with his presentation. And from now here, I will look after the proceedings. Thank you so much, sir, for being a great help.
No. It's a collective effort. Over to you, Mr. Ali.
Hello, can you hear me?
Yes, we can hear you.
Yeah. Okay. So, hello everyone. So I'm going to present today our contribution related to camera and LiDAR fusion for point cloud semantic segmentation. So an outline of my presentation, I'll give a brief introduction and the problem statement that we're tackling, the related work, our approach, the experiment that we did, and then final conclusion. So for the introduction, so when it comes to self-driving cars, they come with a suite of sensors, cameras, lidars, and radars, and they are tasked to obtain self-driving. You have to, first of all, do perception, which means understanding the environment around you. Semantic segmentation is a task, is a perception task in which we try to, for every sensor data, we try to classify which object does it belong to. And so in this research, we're trying to see the LiDAR and cameras, the fusion between them to perform semantic segmentation. So first of all, what's the LiDAR? A LiDAR stands for Light Detection and Ranging Sensor. Its working principle is similar to the radar. It emits laser pulses and it measures the time of flight between the transmission of a laser pulse and its reflection to understand the distance between the sensor and objects in the environment. And so when you emit a laser pulse, what you're getting back is essentially for every laser pulse a point indicated by its Cartesian coordinates, so x, y, and z, and the intensity of the reflected laser beam. So our problem statement essentially is if you have a point cloud, so the array of measurements that's coming from the LiDAR, where each point is again represented by its Cartesian coordinates and intensity. And if you have an image coming from another camera sensor that's mounted on the vehicle, can you classify to which class each point in the LiDAR point cloud belongs? So it's LiDAR point cloud semantic segmentation. Okay. So to do this, there are multiple ways of doing this. Either you fuse the information that's coming from the camera and the LiDAR early on in your pipeline. They call this early fusion, or you have different models processing the camera image on its own and the LiDAR information on their own, and then you fuse on the decision level, and they call this late fusion, or you extract features between from both modalities, and then you do fusion. So this is what's called middle fusion. So in this research, what we're trying to tackle is if you have an image-based transformer, which I'll explain what the transformer is, but a model that's processing the camera image, are the features coming from this model, are they useful for point cloud semantic segmentation or not? And if they are useful, which fusion level between the two modalities performs best? Okay, so I'll go quickly through the related work. I'll talk about what's transformers, point cloud semantic segmentation, how it's done, and the fusion approaches. So transformers are a deep learning models. They have proven very successful in NLP, natural language processing, and their working principle is what's called an attention block. The attention block basically enables the model to attend to different parts of its input based on the relevance of this input to whatever the output that's predicting. Okay. Recently, these transformers have been used or adopted by the image classification tasks or semantic segmentation tasks, and they call this the vision transformer. And what's done here is you have an image, you divided it into patches, and then you feed these patches to an encoder, and then you would have a classification head that basically is classifying the class of the image, so bird, ball, car, or dog. What the researchers from this paper found out is the transformers can perform state of the art, but they need a massive data set to be trained on, like 300 million images. And so a more recent contribution was from researchers at Facebook, they tried to address this massive training requirement by introducing what's called a distillation strategy. So you have a teacher model that's already pre-trained on the data, and you use the predictions from this teacher model to train the transformer model that you have. And so you would have this image broken again into patches, and then you would have a loss coming from a teacher model and the cross entropy loss that you have from the ground truth, and you use both losses to train your deep learning model. And so this is that model is what we will use in our research. We build on that. Now, talking about the point cloud semantic segmentation. So we are talking here about using only the LiDAR data to do semantic segmentation for the LiDAR, so no fusion. So these approaches can be divided by how they represent the LiDAR data to their model. It's either point-based, or they do some kind of a 2D projection from the 3D space, or they use volumetric representation, which uses the 3D space directly. So what the point-based representation approaches are trying to do is essentially teach the model to learn to extract useful feature from each point independently, and use these features to do semantic segmentation or classification for the point to which class it belongs. The 2D projection approaches, they transform the 3D point cloud data into a 2D representation. So either they do a bird eye view, which is dropping the height, and as if you're looking on the scene from a bird eye perspective, and they do semantic segmentation for this bird eye representation, or they do what's called a spherical projection. So you have the Cartesian coordinates for each point. You can tell the spherical coordinates for it, and you can use this spherical coordinates to create what's called a polar grid map, so an image representation of this point cloud, and then you feed this point cloud to your model, and you get the classification for each cell in this polar grid map. Okay, the third way of doing this is using volumetric representation. So dividing your 3D space into voxels and using 3D convolutions to do the semantic segmentation. Okay, the final way of doing that is it combines actually the voxel representation with the point-based representation. So they in their models, they have two branches, basically a point-based branch that works on each point independently. And the idea here is that this point-based branch would detect the fine details for each point in the point cloud, while the voxel-based branch detects the coarse details that belongs to the global scene. And then you do fusion between both of them, and this is the building block that you base your model on. Okay, a final contribution in that regard.
Sorry,
yeah.
I request you to sum up your work within last 2 minutes.
Okay.
Thank you.
I'll jump to our approach. Okay, so we're trying to find if the image-based transformer would help us in point cloud semantic segmentation, and this is our general framework. So you would have an image-based model and the image transformer, and you have the LiDAR model, and you extract features from both of them, and then you can sample the image to get only the features that belong to the 3D points using the calibration matrix between the two sensors. And then you would have multiple losses, either a loss with the ground truth or a KL divergent loss that tries to predict for each modality what the other modality will predict. So trying to bring those two distributions together, or you're trying to learn from the ground truth. Okay. And so we have built 3 different models, one for early fusion, which basically takes the feature from the first transformer block and processes it using this general framework, or a middle fusion model that does the same thing but deeper down this pipeline. And the late fusion model is just doing fusion at the loss level. So we ran this experiment on a popular dataset. It's called Semantic Segmentation, and these are the results that we have found out. We found out that our early fusion model performs best compared to the other two. There's an issue when it comes to the class distribution inside this data set, and you'd see here that the motorcycle class is one of the least represented classes here. It's not detected by either model. And so our conclusion is fusion approaches perform slightly better than the LiDAR only baseline, and you're better off doing early fusion. Yeah.
Thank you so much, Ali. I now request Dr. Bhatt to start with the Q&A session. Thank you.
Other colleagues, if you have some questions, please. Okay. Mr. Ali, are you a faculty or a researcher?
No, just a student, yeah.
So you are pursuing your PhD?
Master's student at the American University in Cairo.
Okay. So when you showed your result, it seems that the fusion is better, like that's what is your conclusion. Marginally, it is better, right?
Yes.
And particularly for motorcyclist, you said that it could not identify or it underperformed, right?
Yes, that's correct. Yeah.
So where was this experiment done?
I'm sorry, I didn't catch that.
And did you take different climatic situations?
No, I believe the dataset doesn't have different climatic situations.
Climate and geographical terrain.
Yeah, so the dataset that we have used, Semantic Kitty, it's recorded from a German city, I think it's called Karach. And yeah, there is no difference in terrain.
Okay. So in terms of those 2 research questions you asked initially, right? What is the final result?
So our first question was whether the image model would help in the fusion, and the answer is yes, it would help marginally. The second research question was which fusion level would perform best, and in our experiment, it was the early fusion.
Okay. So if you have to suggest, let's say, based on your research, if government asks you or some regulator asks you, so what is your final prescription or suggestion to the government, whether they should go for fusion or not? And if yes, what sort of fusion, under what circumstances, what is your final prescription?
So I would say, yes, they should go for fusion. My final prescription would be, yeah, that yes, that you should go for fusion. It would need a significantly larger data set that than the one that we have used in our experiment. And yeah, as you mentioned, that they should try to tackle different terrains and different climates.
Right. Thank you, and our best wishes.
Yeah, thank you.
Please continue such research in future also. Thank you.
Thank you.
Any other questions from the attendees? So with that, I invite the next presenter, Daiki Yamaguchi from Japan. He's going to present his views on improving model accuracy by means of explanation. Kindly start with your presentation, Daiki.
Okay. Thank you, Chairperson. Can you see?
Yeah, you are visible and audible. Please go ahead.
Okay. Hi, I'm Daiki Yamaguchi from Kumamoto University. Today, I will give a presentation titled Improving Model Accuracy by Means of Explanations. First, I'm going to talk about introduction. Second, I want to give a brief background about LRP. Then I'd like to focus on our method and the experiments. Lastly, I will show our conclusions and future work.
Daiki, I request you to limit your presentation within 10 minutes.
10 minutes out. Oh, okay. I
Limit
will.
it to 10 to 12 minutes, right? Thank you.
Okay, I will talk quickly. First, deep learning techniques have been successfully employed in computer vision problems. It is expected that it will play an active role in various fields, becoming an indispensable tool for achieving success. Deep learning has the nature of a black box. This nature is the basis for decisions is unknown due to the complexity of the calculations involved in deep learning algorithms. Hence, it is hard to reason about the decision process that led deep learning to a determined output. Explainable AI is a field that tries to explain models' decisions. With the explanations, no experts can reason about the decision process of a model. For computer vision models, usually these explanations are highlight maps. Our purpose is to make the high-performance model by using the explanation. In this slide, I would like to give a small explanation about a method called layer-wise relevance propagation, LRP. In a general neural network, the input X is multiplied by a weight and propagated forward to compute the output Fx. In LRP, by propagating the output Fx backward, we can calculate the relevance R of each neuron. After all this relevance is captured, we have a relevance map of the input X. When neural network is given an image, it propagates forward and the probability for each class is obtained. When only the probability of a class I are propagated back to the neural network, we can get relevance map of the input X for class I. This image is an original image, and this image is a relevance map by LRP. The relevance map is mainly used for explaining to people. On the other hand, the map captures the features of the original image well. We propose a learning model using this map to train a meta model that uses these features to make predictions. The input to the meta model is a relevance map. When there are K classes, K relevance maps are generated. Arrange them in a horizontal row from left to right in order of class number. In this case, there are 10 classes, so 10 relevance maps are generated. we propose a meta model. This runs the classification patterns of the base model and classification by recognizing the patterns. The input to the meta model is a relevance map generated from the base model. So this can learn classification patterns that the base model got wrong. I will talk about the learning flow of the meta model. First, we train the base model in a general way. Second, a relevance map is generated from the base model. In the end, we train meta model using those maps. In addition, the input to the base model is an image, and the input to the meta model is a relevance map. But the output of both models is a probability vector of classes. For prediction, we tried two approaches. We use the predictions, the first one, meta model only. We use the predictions generated solely from the meta model. The second approach is for prediction is an ensemble. We use the predictions from original baseline model together with the meta model. We quantitatively verify the effect of utilizing our meta model method. We compare the performance gains in terms of accuracy. First, in experiment one, a general comparison. We compared the base model, the meta model, and the ensemble of two models. Next, in experiment two, ensemble weight distribution. We verify the impact of using different weights for the ensemble of the base model and meta model. In this page, we briefly mention the dataset we use. There were 4 datasets and their example images, all with class count of 10. The images are arranged by class from left to right. In addition, the above 3 are grayscale image dataset, but cipher10 is an RGB images. This page is about a result of general comparison. The accuracy of the meta model exceeded that of the base model expect for cipher10. Yes. So we were able to outperform the accuracy based on the information in relevance maps. When unsampled, it outperformed the base model on all datasets. I will discuss why did cipher10 not improve accuracy. The base model uses color information for RGB images and shape for grayscale images for classification. However, relevance maps don't have color information, and color divided regions will be merged like this. We believe this is the main reason that our performance is hard when using RGB images instead of grayscale. This page is the result of ensemble weight distribution. MM0.2 means that importance of the meta model is 20% and base model is 80%. As we can see this table, the accuracy of the meta model alone exceeded accuracy of the base model in all data sets for all weight percentages. This
we
result
just have last 2 minutes.
Okay.
Thank you.
This result shows that the accuracy of the meta model can be further improved by using it as support for the base model. Conclusion and future work. we take one step towards understanding how the explainable AI can techniques be used for purpose other than explainability. We show the importance of using the relevance maps to achieve high performance model. We introduced a technique that is model agnostic and it is empirically shown that our technique could improve the accuracy of deep learning networks. However, since our meta model input is composed of the relevance map of each class, for datasets with many classes, it may become impractical to arrange the images for training. Due to the amount of images, we may need to implement a selection technique for when the number of classes is too high. And that's all I have to say. Thank you for attention.
Thank you so much, Daiki. That was an interesting presentation. I now request Dr. Bhatt to take over.
First, I want if there are some questions from other colleagues, please. There are some previous speakers who also worked on similar types of techniques and models, if they have some question. No. Okay. So just one or two questions only. One is, Mr. Daiki, what is the limitations of your research in case if there are any?
Limitation. Summarize. Let me think.
Sure. Kindly unmute, yeah.
Class, this, here is the limitation. We are our meta model input is complete composed of the relevance map of each class. For data sets with many classes, it may it may become impractical to arrange the images for training. Have I answered your question?
I think, sir, he's pointing towards the last point.
Yeah. Okay. Just one more question from my side. How accurate you think are your results? Accuracy, depending on the type of data set or algorithm you used.
Can you could you repeat? I don't know. I don't follow your questions. Sorry.
Okay. Thank you. It's a good work. Daiki, please continue. Thank you very much.
Thank you.
Thank you so much, both. Up next, we have Vasil Mihai Sushu. I hope I pronounce your name correctly, and I'm so sorry if in case I'm not. So he's from Romania, and he's going to present his views on analysis of an independent double boost interleaved converter in a renewable energy application. I request Vasil to start his presentation. I would also like to reiterate that the presentation limit is set to 10 to 12 minutes. So you're supposed to strictly abide to that. Thank you.
Hello.
Yeah, your screen is visible. Kindly start with the first slide.
Thank you. Good afternoon. My name is Suciu Vasile Mihai, and I am a PhD student at the Technical University of Cluj-Napoca from Romania. I'm here to present our paper intitulated Analysis of an Independent Double Boost Interleaved Converter in a Renewable Energy Application. The aim of the paper, it is represented by a brief analysis of a proposed step-up DC-DC converter, intitulated Independent Double Boost Interlift Converter with 3-level output. Here is shown the proposed and analyzed converter topology, which has been achieved by combining two independent classic boost converters connected in parallel at the input and in series at the output. The converter operation mode has been analyzed in the context of a photovoltaic application in which the converter power stage has been used as an interface between three photovoltaic modules connected in series and the deserved load. A series of tests of the DC-DC converter were performed in two study cases. In first case, a co-simulation using MATLAB Simulink and Plex block set has been done. Here it can be seen the block diagram related to the simulation model developed in MATLAB Simulink in conjunction with the Plex block set. By using Plex block set within MATLAB Simulink, a co-simulation approach of the control law and the DC-DC converter power stage has been done. The control law, which has been represented by the perturb and observe maximum power point tracking algorithm used to extract the maximum power from the PV array, together with the PV modules, has been implemented using MATLAB Simulink native toolset. The power stage of the analyzed DC-DC converter has been implemented using a Plex block set add-on. The converter load it consists of a variable resistor, and the equivalent resistance of the deserved load has been modified in such a way that the output voltage was maintained constant at 400 volts, regardless the system output power or solar irradiation level. The co-simulation model implemented using MATLAB Simulink is shown in this figure. The model consists of the PV array block used for emulating the characteristics of three Canadian solar panels connected in series, the perturb and observe MPPT algorithm subsystem, whose diagram it can be seen here, and the DC-DC converter power stage subsystem, who's implemented in Plex block set. Again, the DC-DC converter electronic diagram, it can be seen in this figure. Multiple simulation of the power stage operation were performed and recorded for the cases in which the profile of solar irradiation across the PV array had different values, such as 600, 800, 1000, or 500 watts per square meter. The temperature of the PV modules has been set at the value of 25 degrees Celsius. In the left figure, or in the figure A, are shown the waveforms of the PV array power, the voltage at the terminals of the panel group, the current through photovoltaic panels, and the duty cycle of the DC-DC converter. These are presented in relation to the different values of solar irradiation across the panels. It can be seen that the PV array input power and current are changing with the change of solar irradiation levels. In the right figure, we have the DC-DC converter inductor currents and also the output voltage and currents of the converter presented for different values of solar irradiation levels. in relation to the duty cycle of the converter. Because the output voltage was maintained constant at the value of 400 volts, the inductor and output currents are changing with the change of power, and the change of power occur at the change of solar irradiation levels. In the second case, an online real-time rapid control prototyping simulation using a digital signal processor from Texas Instruments with a JTAG connection to a host computer that runs Altair embed software has been done. In the right figure, we have the electronic diagram of the experimental model. And in the left figure, it can be seen the laboratory test setup used. The characteristics of the 3 Canadian solar panels connected in series were emulated using a bidirectional power supply with solar panel emulation capabilities. The deserved load consists of a variable resistor, and the equivalent resistance of the deserved load has been modified in such a way that the output voltage was maintained constant at 400 volts, regardless the system output power or solar irradiation level. Here we have the experimental results of the practical measurements recorded in Altair embed environment. And we can see here the waveforms of photovoltaic array power, the voltage at the PV array terminals, and here we have the current through the photovoltaic array panels. These are presented in correlation with the duty cycle of the converter. And here we have the different values of the solar irradiation across the PV panels. Also, here we have an oscilloscope representation of the converter waveforms at the value of solar irradiation of 1000 watts per square meter. Here we have the inductor currents of the converter. And in the figure B, we have the input and output currents and voltages of the converter. Also, here we have the efficiency measured of the power stage for different values of input power or of PV array power. We can see that the maximum efficiency of the DC-DC converter, the measured efficiency, is achieved at the power of 540 watts. In conclusion, this work emphasizes an analysis of an interleaved boost converter with 3-level output working in a renewable energy application. Also, a maximum power point tracking algorithm was implemented in order to extract the maximum power from the PV array. The operation of the converter has been analyzed using the voltage and current waveforms in different operating situations, and also some efficiency measurements of the converter DC-DC power stage has been done, obtaining promising results. Here there are some of the reference used for this work. Thank you for your attention, and if there are any questions, I'm happy to try answering. Thank you.
I would request Dr. Bhatt to come up with his queries.
First, again, anyone else, if you have some questions? Okay, so good work, Mr. Vasil, and best wishes for your PhD work. Just two questions. One is towards the end, you said that it delivered promising results. So in nutshell, what are those promising results? Quickly.
We are refer at the efficiency of the converter. When I'm telling we have promising results, we are referring at the efficiency that we have on this DC-DC power stage working in this condition.
So how much
also,
how much is this efficiency increase?
In this paper, we are not doing a comparison with another DC-DC structures.
Okay.
So I can't tell you for sure how we can increase the efficiency using this type of converter in comparison to a classical boost converter or an interleaved or a classic interleaved boost converter.
Thank you. Best wishes.
Thank you very much.
Thanks again. I would like to call now Yuxi Jin from Japan. Her paper is on multilingual complementation of casualty property on Wikidata based on GPT-3. Yuxi, the mic is all yours. Kindly start with your presentation and stick to the time limit, which is 10 minutes.
Okay.
Please start your screen share. We could see a glimpse of that.
Okay, can you see that slide?
Not now. Previously, it was visible.
Oh.
Try once again.
See, it was visible. Yeah, I think it has started now. Yes.
Okay, I'm sorry. What it?
Yeah. It's visible now.
Yuxi, can you turn on your camera, please?
Okay, and wait a minute. Can you
start? Yeah, we can see you as well as the presentation.
Hi, I'm sorry about it.
That's absolutely.
And at first, please let me introduce myself. My name is Jin Yuxi from Nagoya Institute of Technology. And today I want to talk about our research, the title of which is Complementing a Causality Property on Wikidata with Extracting a General Causal Relationship from Multiple Text state. And let's begin with the background and the purpose on our research. In recent years, people have become more and more concerned about the social problem, and we aim to develop the agents for understanding distribution, public opinion, and preference. For this development, the agents need to have a causality knowledge. Meanwhile, Wikidata serves as a knowledge based on provide linked data. Its precision of the causal knowledge plays an important role in the analysis of the social issues. However, the current situation on Wikidata that most of the entity has no causality content, and some of them the value of is wrong or only a causality in a specific situation, which can't be widely used as general knowledge. Therefore, how to automatically extract general knowledge is our task. Then let's have a look about the problem analysis. First, the various model of the extracting causal relation are for the single causal, which is dependent on the sentence itself. For example, Mac get headache after drinking. Headache and drinking is singular causal relation. And this relation can't be ended to the wiki date. Thus, we need to predict general knowledge. Second, is impossible to infer causality exactly correctly. Thus, we need to predict the general knowledge. So the reliability score of the inferred answer is calculated and ranked. Even wrong answer can be eliminated, and thus correct general causality is inferred. Third, due to the language characteristic, the inferred results are limited by language and culture. So using multiple language for inference can increase the credibility of the general effects. Therefore, in our study, extract the singular causal from multilingual text at first, and then we rank the result predicted with the reliability score to obtain the general causal relation. Next, let's take a look at the implementation. The implementation of this paper is carried out in 4 processes: collecting data, training model, testing model, and applying the model, as shown in this figure. We use the web scraper to collect social news is from the Google English News, Japanese, and Baidu News, contain the word A, and then use the crowdsourcing to artificially determine effects into the news due to the word A. And then we use the GPT-3 model for training. And in the testing step, since the reliability score were calculated afterward, the required verification metric is the precision. Finally, to get the general causality, we take the entity alcohol as an expansion. We prepared new data and once again use the model for prediction. The effect of the prediction that there is an answer will be preserved for the next process. The non-effect in the prediction has no meaning for the calculation of the general effect afterward. All of them will be removed. These are the singular causal relationship we get. Next, to detect the general causal relationship, we group the results and calculate the reliability score. All the speculative answers were grouped and processed. The similarity calculation of the odd answer was calculated, and the answer with similarity greater than 0.6 were divided in the same group. Last, each group of the reliability score is the multiplication of the TF, IDF, and the precision of the model. In our work, we have 3 experiments and set the 2 comparative analyses. The 2 sets of comparison will conduct the verified the impact of the number of the model on the result and impact the form of inputs on the results. In the experiment 1, we input Q and A like this, and we train 3 models use English, Chinese, and Japanese training data respectively, and we get 74.54% precision. Japanese and Chinese are precise with the MICAP and JBA before the similarity grouping process. Table shows the high frequency phrases in the 3 languages that predicted output due to the alcohol. Due to the language characteristic, the frequency of the results from each language are different. The TF-IDF of the group of the words with the same meaning in the 3 languages superimposed and obtained the reliability score of the effect of the group. This step was superimposed artificially to calculate the reliability. This is a complicated precise and required artificial classification, which can interfere with subjective judgment and affects the accuracy of the reliability score. Unlike experiment 1, experiment 2 puts all the data of English, Japanese, Chinese together, and overall precision of this model is 74.65%. And we use the Google Translate.
Sir, with your consent, can we move to the conclusion part, if you allow?
What's wrong about it?
I don't know. I'm just asking the session chair.
Yeah, please. Because our scheduled time itself was like 4:30.
It was 4:30, right? Yeah. So we just have 4 minutes. Will you please come to the conclusion part? Thank you.
It's a wonderful work you have done, but just time is the constraint.
Okay. And we use the Google Trans to automatically trans results from the 3 language into the English uniform and gets the and we can get the precision of the 74.65%. And in the and experiment 3 is an improvement of the form of the input station. The original Q&A form was changed to the simple expression of the cause and effect. And we has the precision 76.29%. Experiment 1 is the composed of the 3 language model, and experiment 2 is the one model that puts 3 language together for training. The comparison verified the number of the model can have an impact of the experimental results. And we can know that experiment 2, the overall precision of the predict the effect of the entity is higher, and that one is the 3 language training together, so it's more convenience and consensus. Experiment 2 is use the Google Trans, this API translation. The 3 language can be translated into English before the TF-IDF calculation and can be more convenient. And experiment 2 and experiment 3 were compared to verify the impact of the input from the experimental results. And the experiment 3, the input date is more convenient. And we can know that.
Please. All right, thank you. Yeah, please conclude it. Yeah.
And we can know that the experiment 3 and the prediction is high, and some of the results some of the predicting results are mixture of the language. So maybe in the next work we will set some language restriction. And in the last one is the conclusion and future work. And in this paper, we propose the model of the inferring causality using the GPT-3, in which more is the more concentration was used as the input data, and 3 language were training together, and we get the highest precision of the 76.29%, and the wrong result was excluded, and general causality was obtained by ranking. And
so you see it's a good work, and we congratulate you.
Yes.
So our best wishes, but only one question. In the future work you are writing that this can be used to predict the value of other properties.
Of course, in this.
Which are the other properties?
And in this this time our research is just try to extract the property of the cause. But I think in the next work, maybe we can extract the reason, results or other property to complete the property in the Wikidata.
Okay. Thank you, Yuxi. All the best.
Thank you for your question.
It was a very good work. Thank you.
Thank you so much, Yuxi. That was a wonderful presentation indeed. Thank you so much. I now call the next paper presenter, which is the last presentation of the session, Suleiman U. Hussein from Nigeria. His work is entirely based on robust stabilization of ball plate system with higher order SMC. I would request him to stick to the time limit of 10 minutes. You can start your presentation. Thank you.
Okay. Good morning.
Yeah, good morning.
All right. I'm
Please make
Hussein
it full screen.
Suleiman Usman. I'm presenting
yeah, thank you.
robust stabilization of plate system with higher order SMC, that's sliding mode control. The outline is I'll start from introduction, the focus of the work, the ball and plate system model, then controller design. Then my result will focus on system response with classical sliding mode control, system response with smoothed sliding mode control, then system response with recurrent element neural network optimized sliding mode control, then steps response with smoothed super twisting sliding mode control. Then I will compare the work. Then there will be conclusion. Then I'll talk about future work. Then references. Yeah. What is stabilization and stabilization control? Here we say stabilization is one of the major goals in most control system design. Hence, stabilizing the ball precisely at a predefined point is a very critical challenge. Then the difference between stabilization control and trajectory tracking. Here we have for stabilization control, we are talking about specific position. While for trajectory tracking, we're talking about follow a predefined path. The concept of ball and plate system, you have a ball on a plate, which is supported by a hinge, then controlled by two motors. This will be seen in some slides ahead. So importance of the system is used as a test bench for nonlinear dynamic problem, trajectory tracking, and also it is employed in testing different control algorithms due to its under actuation instability, and it can be applied when designing controllers in areas like unmanned aerial vehicle, rocketry, satellite attitude control systems. And the aim of this work focuses on stabilization of the system with respect to bounded disturbances. Then different controllers are developed to test the different control algorithms. And we are looking at the rise time, steady state error, percentage overshoot, and disturbance rejection. Then the basic concept of the ball and plate system is you have a ball, a flat square plate, then the camera, then a 2 DC stepper motor, then using the Euler-Lagrangian generalized equation to achieve the model of this system. Then you have the model of the DC motor, and by the time you impute this parameter, you get this transfer function. Then this is a schematic diagram, figure 1, the schematic diagram of the ball and plate system. Then for the controller design, a double feedback loop system was adopted for the design, where for the inner loop, we have a PID controller, which is tuned with weighted artificial fish swarm algorithm. Then while the ball position is controlled by the SMC, which is the outer loop. And the outer loop was first controlled by classical SMC, after which it was replaced by smoothed SMC, then recurrent L-man neural network as SMC, then finally smoothed super twisted SMC was employed. So this is a block diagram of the inner and outer loop control design. So, and these are the results. As you can see, the system response with classical SMC, you can see that the ball was able to be stabilized. And when disturbance was introduced, which is 0.4 step disturbance, the system was unstable. And these are the results. The overshoot is 0%. Then when the controller was replaced with SMC, you can see the ball too, we're able to stabilize the ball. However, when there was disturbance of 0.4 step input, at this time, there was a steady state
Dr. Hussain, are you here?
Yes, I can hear. Yes, I can hear you. Can you hear me? All right. So there was a steady state error. However, the system is still stable. Then when the smoothed SMC was replaced with recurrent element neural network optimized smoothed sliding mode control, you can see the result. The ball will also achieve stability. However, when we introduce a disturbance of 0.04 step, there was a steady state error. But when the magnitude of the disturbance was increased to 0.4 as a reference, the system became unstable. Then also, when we use the SST-SMC, that is the smoothed super twisting sliding mode control, we're able to achieve stability. And when we introduce 0.4 step disturbance, we're also able to achieve stability as well. And the steady state error here is 0. And even when the disturbance was increased to 10 step disturbance, we're still able to achieve stability. This shows that the smoothed super twisting sliding mode control is more robust over the other controller. Then this is a response to show how robust or better the SST-SMC is over the rest of the controller. And this table shows that the SST-SMC is better. As you can see, it has a very fast response time, and the steady state error, we had none, even while the disturbance was increased to 10 units. Then in conclusion, in this work, bus stabilization has been achieved with all design SMCs. However, the SST-SMC showed a better robust stabilization and disturbance rejection ability for the ball on the plate over the classical SMC, SS-SMC, and Reynolds SMC. Therefore, the SST-SMC is better for robust stabilization of the ball and plate system. Future work will be looking at trajectory tracking of ball plate system with different design SMCs, which will be considered. Then comparison will be done to determine the best in terms of robustness and tracking error. These are some of the references. Thank you for listening.
Thank you so much, Hussain. I firstly would like to say that a special thanks to you to conclude your work on time. So thanks for that. I would now request Dr. Nitesh Bhatt to please come up with his queries, if any.
Anyone else, if you have a question from Dr. Hussain?
I don't think so, sir.
Okay, good work, Dr. Hussain.
Thank you
Very
so
good
much.
work, and you concluded your work in time. Thank you very much.
Thank you so much.
I would now request the session chair, Dr. Nitesh Bhatt, to give us a special remark regarding the presentations covered in